seminar. Today we have Claudia Sawyers Gallo. The A has a Catalonian accent on it. She's going to be talking about algorithmic randomness. So,
Well, hello everyone. So today I'm going to present to you basically about, this is going to be a talk about randomness. So we talk about randomness all the time. Like in the study of probability, we talk about random objects. We say, oh, let's assume this random distribution for this particular phenomenon. Or, oh, take this set of random events and let's study them in some particular way. But the thing is, when we stop to think about it, mathematically, what does the thing being random actually mean? Like, how do we know whether something is actually being random or just following a set of very specific, like an algorithm kind of thing? Let's consider, for example, let's consider some sequences, some infinite sequences, right? Let's consider, for example, this one. Or, for example, we could also have this one. Or we could also have something like this. I don't know, just making it up. Right? The thing is, in the notion of just probability theory, all of these sequences, imagine they're tosses of tails, of heads and tails from a coin, in a coin that has been tossed infinitely many times. From just a probability point of view, all of these sequences have the exact same probability of being produced. All of them have probability 0 of being produced, actually. So in a way, we cannot really tell whether one is more random than the other one. However, I asked the audience, does your intuition tell you that one is more random than any other?
Yeah, I mean, the third one seems more random than the
Mm-hmm.
first one. Look at the pattern.
Oh yeah, what is the pattern?
Pattern is you just alternate between 0 and 1.
Mm-hmm.
Maximum over here, you keep counting an extra 0 every time you're off.
Exactly. So we're seeing a sense of a pattern in the first ones, where the second one feels very irregular in a way. It doesn't follow any sort of intuitive kind of sequence, right? So here's when we are going to introduce the kind of, because we're building the tools, right? We're building the tools to be able to differentiate between what we feel to be random, the things that don't really feel to be random. So we have some like requirements, and one of them, as you've said, some requirements. The first one that you said is a sense of local irregularity. Right? We want that when we take an infinite sequence that we look at a part of it, it doesn't seem that it has some sort of pattern. We want to maintain this sort of irregularity throughout the whole sequence. But at the same time, if we consider the whole sequence as a whole, we want at the same time that the sequence is extremely regular, as in it looks the same everywhere. For example, because if we had an infinite sequence and part of it has a significant increase in the distribution of zeros, for example, compared to a different part of the sequence that has significantly more ones, there is a sort of property that we can distinguish that tells us, oh, perhaps that coin wasn't actually fair. Perhaps after a certain point, it starts just producing more ones, right? That doesn't really feel like a random process. So we also want to add the notion of global regularity. So despite being rather paradoxical, that we want to be able to kind of join the notions of a randomness being something that is extremely irregular, that you can't predict, that you can't compress in some way, but that at the same time has extreme global regularity and is just something that it is a constant process after all, right? So there have been several attempts to obtain these kind of tools. Some of the first ones were by Borel in the early 20th century. He was playing with some sequences of infinite sequence of real numbers, and that satisfied the law of large numbers, and he was able to do some things with the distribution of the digits, but it wasn't quite there, and there were like many sequences that were able to pass all those tests and still, have some sense of irregularity. And the same thing happened with von Mises in the 20s and 30s. He also played with the distribution of zeros to ones, basically, but he also introduced notions of taking subsequences of them and also seeing the limit of the distributions. But this is just for you to look, is a very interesting development of the idea of randomness. But today we're gonna only take a look at let's say, if you ask someone in the area or tangential, if a sequence is algorithmically random, they're basically gonna think of this specific type of randomness. It was the one that was established around the 60s. It was basically the start of the whole area of algorithmic randomness, which basically tries to classify the types of randomness, tries to be able to precisely describe this. And as we will see, especially if there is a next talk, if the host here wants me again, if in the next talk I would like to talk more about different notions of randomness. Today we're going to fixate on one, but note there is actually no fixed notion of randomness. It is not as an absolute notion as we would like it to be, but it also makes it more interesting. So today I'm going to present on the 3 standard paradigms of randomness. So there's 3 standard paradigms. Paradigms meaning kind of approaches. In a way, these paradigms answer 3 different intuitions to how we think these sequences should behave. The first one is the incompressibility. Is the incompressibility paradigm. This one answers our intuition that a sequence is random if and only if we cannot compress the information. Basically, if you have basically just a bunch of zeros, just a sequence of infinite zeros, you can somewhat compress the information and just say, oh, it's just a sequence with all zeros, right? That amount of information is much, much smaller than what you need to actually describe something that is, actually a random behavior. Something, accidentally made one that seems rather, non-random, but it's fine. You get what I mean. It tries to account for that sort of intuition.
But the second one you wrote was more compressible than the first one, right? The first
yes,
one
exactly.
the row was all zeros.
Exactly. There's a sense of a hierarchy of how different sequences are in terms of how much it takes us to describe them. And we would want infinite sequences to be really hard to describe, as in there's no sort of algorithm that would allow us to just produce them. The second one is the unpredictability. The unpredictability paradigm. This one answers the intuition that we would want our random sequences to be fair, as in we don't want to be able to predict how the sequence is going to go because it is a random sequence that we have. Well, we shouldn't be able to predict how it's going to behave, right? And thirdly, it's going to be the measure theoretic typicality. Measure. Oh my God! What is? Forgive my handwriting. Measure theoretic typicality. This basically answers the idea of global regularity intuition. The idea that a infinite sequence that's random has to have no peculiarity to it. It has to cannot have a particular property that we can pinpoint and that we can actually describe in some way that it wouldn't make it random, but rather that is very typical, right? It is very homogeneous throughout all of its length, and it basically this paradigm is also equated with the idea that a random sequence should be able to pass any sort of statistical test, as in like, oh, see the distribution of 1, see the distribution of 0, how do they compare? All of the tests that we're able to say about randomness should be able to be passed in this sort of paradigm. However, note, and this is going to be a result that we will discuss perhaps later or in a future talk, is that these three notions, which by the way are attacked by three completely different areas of mathematics. This one is through complexity theory and information theory. This one is through probability theory and through the construction of martingales that we will talk a bit later. And this one is through the language of measure theory. Like these were they weren't completely independent, but they were developed kind of at the same time through completely different methods. And they all happen to be completely equivalent. So that's, it's a really nice way to see how, in a way, math, these definitions answer to, in a natural way, to what we want them to be. These definitions of randomness are not just made up, but rather satisfy actual basic intuitions for what we want them to be, right? So now that I'm done with the introduction, okay, in this first talk, we will mostly consider the incompressibility paradigm, especially because it has actually really nice tools that also appear in many other areas of mathematics. We'll briefly mention the unpredictability, but we will not talk about the measure theoretic typicality, but we could make another talk just explaining the whole thing, because it is far more detailed in its construction. So yeah, let's start with the incompressibility paradigm. So again, this one answers the notion that a string is random if and only if it is incompressible, as in that the only way to generate that string with an algorithm is that the algorithm inherently already has the information about the string already, right? Of course, we can create an algorithm that just feeds into the infinite string and just outputs the infinite string. That's fine, right? But we don't want to be able such that a shorter version of that infinite string to be able to be fed into a machine that produces the infinite sequence. That would mean that in a way the information of the infinite sequence has been compressed, and thus there is a sort of rule that can be exploited in some sort of way. So just to give you an idea, let's consider the example that I just put before. They just have 10,000 zeros, right? Here we could just create a machine that says, and here, by the way, machines, I'm referring just general Turing machines. This is the type of objects we're going to be dealing with in this paradigm. Just a machine that says, just repeat 0 just 10,000 times, right? And that's definitely going to be able to be described, both the machine and the code, in less than, for example, 10,000 digits, right? Like 10 bytes, bits. But instead, if we have a sequence generated by 10,000 coin tosses, then there is this sense that there is no algorithm for it. There shouldn't be an algorithm that actually is able to produce all of it with like, I don't know, 10 bits or something. It shouldn't be possible if it's actually a random sequence. But before we get into the infinite case and we treat infinite sequences, we will first consider finite strings. And here we will introduce the notion of what we call plain cumulative complexity.
Sorry, so one of them is a string, the other one is a collection of strings.
No, it's one coin toss, as in 10,000 digits that are randomly zeros or ones. It's one coin toss is a 0 or a 1.
So the algorithm is supposed to kind of predict what it is, but it can't.
No, here is more like we have produced one that's set. Now we want to build an algorithm that produces that specific string.
But it's
You can always make one that produces it, yes. But the thing is that an algorithm that produces 10,000 times 0 is going to be much shorter than one that produces one that has been produced by 10,000 coins.
So like worst case scenario here, you have to store all the bits, set up a big file, whereas here I can just make a small file with a score.
Exactly. You will still be able to compress part of the information because we are dealing with finite strings. Yes? Well, you're going to see, we're first dealing with finite strings. We'll see exactly what we do with infinite strings, but it becomes a limiting process. We don't deal with the whole, infinite, but we kind of go, we take the first n parts of the sequence and see that it has to satisfy certain conditions. We will talk about it, though.
The incompressibility came from the need for implementing randomness in computers, right?
Yes, and there's actually going to be a bunch. I know we're going to ask about applications, so I brought a bunch of applications of. Actually, this is one of the ones that has most applications in wanting to introduce actual things that are demonstrably random or like computably random into be able to test things in computers and stuff. But yeah, let's talk about the actual constructions, the mathematical constructions.
So it's like incompressibility kind of compares like, oh, I have one algorithm that produces random strings, I have another algorithm that does it in a different way. It kind of compares. It's sort of a metric for how you.
No, it's a metric on strings, not on algorithms. Mm-hmm. You have a string, and you can say how complex or not. Let me build up the tools, and then we can talk about exactly how. So we're going to have a notion of plain Kolmogorov complexity. Also plain because we're going to introduce a different notion of Kolmogorov complexity in a bit. So let's consider M to be a Turing machine. And we will define the Kolmogorov complexity on a string, on a finite string. So the plain Kolmogorov complexity of a string with respect to M to be the following, right? It's going to be some function here in terms of theta that is going to be defined as the minimum length, right, of this string. This is actually, what is this, tau?
Yeah, tau.
Okay, this string tau, where tau is also a finite string, such that this Turing machine, when fed tau, is equal to our desired string, right? So what is this saying, basically? Let's take this particular machine. Let's imagine, for example, let's write some examples here, right? Let's consider the machine that for every single input just outputs its own input, right? Then we want to consider all the possible inputs we could introduce here, such that and the smallest size of those inputs, such that one gives us our sigma, is going to be the complexity. As in, what is the shortest input that I can give this? It's like a number, right? Like if it's 3, it means that the shortest input that I can put is of length 3. So for example, for this particular machine that just does that, we consider the string 0101. Okay, what is the complexity of this string? Well, since this machine just outputs its own input, we will never be able to produce a smaller string that put here will give us the original output. So this one, actually the only input that will give us sigma is going to be sigma itself. So the complexity of sigma is just going to be the length of sigma, which in this case is just 4.
I'm sorry, so M is a function from your Cantor space to Cantor space? A Turing machine.
A Turing machine? Oh, I didn't want to get into the notion of what a Turing machine is. Yes, it's, you basically consider just a general notion of what a machine is. You put in a finite string, and then in the tape of the machine, if you could imagine, it then leaves something at the end, and that's going to be your output. Yes. So yeah, I didn't want to define what M was, but your complexity is just a function basically from finite strings to natural numbers. It's just going to take them in. And oh my God, I forgot. If what is it? It's in the case in which the machine doesn't actually give you anything. If there doesn't exist tau in the domain of the machine, such that m of tau is equal to sigma, then we say that the Kolmogorov complexity of that string is just infinite. We just define it that way, because that could also happen. Like the machine, for example, the machine that doesn't halt for any input, right? And yes? Well, here in plain Kolmogorov complexity, we're just considering any sort of Turing machine, the general class of Turing machines. And this Kolmogorov complexity is in terms of M. So we say, if we want to be able to say that a string is random with respect to M, if it satisfies, so is this too low? Okay. We say that a string is random in respect to M if it satisfies this. Right? The idea that the shortest string for which you could ever produce that sigma has to be bigger or equal to the size of itself of sigma. This is what we were saying. And a string is going to be random if the machine already has the information about all of the string in itself, and there's no way of shortening it in a way. Let's consider, for example, not a counter example, but a distinct example. Let's consider the machine that does this. Wait, that's supposed to be a sigma. And this is just concatenation, right? Then, for example, for the very same string, right? We could just, let's consider tau to be just, bad example. Let sigma equal 0, 1, 0, 1, 0, 1, right? Then we could let tau just be 0, 1, and this machine with input tau would produce 0, 1, 0, 1, 0, 1, which is just sigma, right? In a way, here the complexity of sigma in terms of this particular machine is going to be 2, right? It's going to be this. Okay. It's going to be 2, which is going to be the shortest thing that we can put here such that it produces sigma, right? Which, as you can see, is smaller than the size of sigma. So in a way, the information of sigma has been compressed in this machine. So in this way, sigma is not random with respect to this machine.
So M sort of composes the rules that you use to construct. So if I'm given the string, right, and I want to find a rule which constructs the rest of the thing, that's encoded in this.
No, we're not constructing the rest. This is just finite strings.
Yeah.
This is just a machine that turns strings into other strings.
So if I'm given 1,000 digits, right?
The output could be the machine that always outputs 0. You could feed it 1,000,000 digits, it just says 0. This is just machines, and this is just one that talks talks about randomness with respect to a machine of finite strings. Here we're not considering the infinite case, and we're not saying anything about constructing the rest of the sequence.
No, but does this definition encode the notion of incompressibility, right? So
with respect to a specific M, but yes.
Yeah, so if Cm of sigma is very large, I would say that's very
if what, yes, exactly. If the only thing that you can feed into this so that it actually gives you sigma is this enormous, gigantic thing that tells you, oh, maybe first do a 1, oh, but change it to a 0 then. Oh, but then change it again to a 1. Like this whole thing. And this is the smallest way you can actually describe sigma through this machine. Then yes, the complexity of that string is going to be very big in respect specifically to the size of sigma. Because sigma could be a really small, well, yes, it's fine. But yeah, any more questions? Okay, so now let's try to take away the dependence that now we've introduced into M. Now that we have the notion in respect to a very specific machine, let's try to eliminate this specific dependence by introducing this plane cohomologous of complexity, but in relation to a universal Turing machine. For whoever doesn't know what a universal Turing machine is, basically just a Turing machine that can simulate any other Turing machine that you want. Basically, every Turing machine is, we can describe them in a countable way. So you could simply just make an assignment of Turing machines to natural numbers. You can have a sort of encoding. And for example, a Turing machine basically is such that a Turing machine, U, is a universal Turing machine, or what we call UTM, okay? If for all Turing machines M, there exists some specific number, okay, some specific string, some finite string, such that for every single input that we could put into that machine that is also a finite string, we have this sort of relation. Basically what it's saying is that if we fix some particular machine, there will always exist some particular string such that basically you just put the string before every single input and they will behave exactly like the same machine. They will have the exact same output. This is the idea, that for every single machine this is possible. In a way, we're encoding the information of all possible Turing machines into a single one, right? So now we're going to fix our definition of cohomologous of complexity so that it takes away the dependence, right? We take away the Turing machine, and we say, fix a universal Turing machine U, okay? The thing is, there are several ways in which we can encode this U, right? There's several ways, several encodings. And actually, the plane cohomologous of complexity that we're going to build is going to depend on that particular choice, but we're going to see how that particular choice is actually not going to be, it's not going to be relevant for us when we are trying to define randomness. So let's try to fix it first. Okay, we fix a universal Turing machine, and now this sigma, the plane cohomologous of complexity of this string, now without any respect to any machine, is going to be defined, and we drop here. We could write a U, but we drop the things because we're generalizing it to any machine. The plane cohomologous of complexity of this string is going to be defined in the exact same way, except for the fact that here we're just going to change the specific M to this particular universal Turing machine that we've created. Note again that, and we have the exact same definitions for universal. However, note that since we have the construction of the machine that just outputs its own input, we know that there will exist some machine that outputs any input. So remember this thing that we made to avoid the infinite case? Well, it turns out for a universal Turing machine, every single input is there is going to exist a machine, at least just the identity machine, that is just going to produce that input. So we don't even have to care about this case, because for this generalized form of plane cohomologous complexity, this one is always strictly smaller than infinity. And in the same way, we define a string to be random if the plain cumulative complexity of that string is bigger or equal to the size of that string. Any questions? Yes?
Yeah, so this string includes the coding of the Turing machine that's actually going to do the job, that universal Turing machine is going to stimulate, right?
Wait, repeat, sorry?
This tau, right, is going to include the first part of the tau of the string is going to include the coding, right?
Yes. This is important to note. Yes, continue.
So what if the machine is just difficult to code, but it itself is easy for it to output the string? Like its complexity is actually really low, but it's just like to actually write the code for the machine, the string can't.
Yes, that's very true. That's why the choice for you is still going to influence the specific number for which this is true. In fact, and this is precisely the reason why we don't really care about the encoding of U and the way we completely avoid this problem is by the fact that for any Turing machine, right, for any universal Turing machine U, it is going to be true that the plain cumulative complexity in terms of U is always going to be smaller than the plain cumulative complexity plus some specific constant based on some specific machine. This is for all single machines, right? This is the actual thing I was saying, where you know, C is just a natural number, it's just a constant, right?
So does C sigma have an upper bound? Easy upper
No,
bound?
we're not. Again, we don't really care about this specific number because, again, that number, the very specific number depends on U, right? Depends on U and sigma. It depends on so many things that it's not actually useful to try to actually compute this. But we can do math with the concept because the actual number doesn't really matter because of this. For any particular choice of U, this is always going to be satisfied. That is, it will be able, every machine, think about the specific, what you were saying, the encoding that you have to do of the machine to put it before. That's going to be the constant that's going to have into its factor. But we're going to see that this constant does not matter. The idea of constants in this whole paradigm are not really that important, because we're going to be able to establish whether something is random up to a very specific constant. You will see, I think it will make sense. The whole point is just remember that we can always reduce everything here just by a constant. It's just the difference between the most efficient machine and the universal one is just going to be the specific constant that's going to be the constant that is required to encode it. Yes?
This is also for all sigma.
Yes, for all sigma.
So this is like another way of saying forget about the coding for the machine, just for the tau.
Yes, exactly. This is forget about the coding. Well, you shouldn't really forget about the coding right now, but you will see that C doesn't matter. That's when we're saying the coding doesn't matter, because that specific C is what tells you, it's what corrects for the coding. So yes. I don't think we're going to, I had the proof of this. I don't think it's going to be.
Just to clarify,
Yes.
I think you said it. So C is sigma infinite?
Yes. Let me just write it for the sake. This is also, yes, it goes, the quantifier goes before, but for all sigma. For all sigma and for all M, there exists some C such that this is satisfied also for every single, for any single choice of U. So now we're trying to, now we're going to use this concept that we've just built to build the infinite notion of what it means for a string to be random. And yes.
Just to then this like
Oh, you mean that the sigma goes after? You're right, I'm sorry. Oh, sigma. Thank you. So yeah. Okay, now that we've given the tools, I wanted to ask if there's any guesses of how we could generalize this to account for an infinite sequence. You've seen it?
Maybe truncate, right?
What do you mean truncate? Like you just forget about the...
Yeah, you take an infinite sequence and you just truncate by n sequence of those numbers.
Exactly. So in a way, you're kind of taking the first n parts of the sequence, and then you want to basically have a condition of it. That's exactly what we're going to do. That's basically, we're going to say an infinite sequence W, right? I don't know what I wrote, infinite, but yeah, an infinite sequence, omega, sorry, is random if there exists some constant d, okay, such that the cohomologue complexity of that string in the first n values, right, is bigger or equal. Here we would just say, right, before we just said the size of n. Well, not the size, just n, right? But because of that fact that we have to account for the correction of the codes, now we want this condition to be met through, so we account for that by subtracting some specific constant, right? Oh, for all n. Yes. Right? So for some string, there exists some constant for which we can just reduce massively that other side, such that the cohomologue complexity of that string is always going to be bigger or equal to the size of the amount of stuff that we're taking, minus a specific constant that takes care of the specific encoding, right? So we look at this and we're like, this seems like a sensible notion of randomness, right? We're like, if we take a really, really, really big enough string, this constant doesn't even matter anymore, right? Like if we take enough of a first chunk of the string, that constant doesn't even matter. And in kind of the bigger chunks we get, the less it matters, and the original notion of cohomologue complexity is still there, you know? For something that isn't random, then it doesn't matter how much we reduce it at the beginning, because eventually we will be able to catch up, and we will be able to reduce it eventually for the cohomologue complexity to be smaller than this specific number. So this seems like sensible notion. However, in 1966, by Martin Loaf, he proved basically, sadly I guess, that for some specific omega infinite sequence, for all d, there exist infinitely many n inside of n, such that precisely that is not satisfied. As in, for any single infinite sequence, there doesn't actually exist this constant that allows for the cohomologue complexity to maintain this relationship for every n. And the reason is because Turing machines are too powerful. For any single infinite sequence, there is a conceivable Turing machine that could potentially compress the information of the infinite sequence, even in the kind of this limiting process that we're doing. So what do we have to do? Is just reduce the power of the Turing machine. So we're going to reduce the the types of machines that we're going to be able to use in order to be able to actually differentiate from the random and non-random sequences. Because now, with this definition, all of them are random. All of them are non-random. So we're not able to actually distinguish them. And for that, we have to introduce the notion.
That's funny. So this definition you introduced before finding specific random sequence. Yeah.
Huh?
This definition was introduced before actually having an example of a random string.
Well, actually, with the finite notion, there is a proof that there exist random sequences. Like for any, right? I think there is.
She's saying this specific definition. There's nothing that fits.
Yeah, there's absolutely no single sequence is random according to this definition. So it's useless to us. This is just too sensible in a way. This is the type of thing that tells, oh, this infinite sequence, oh, you could just kind of, compress parts of that thing in an infinite kind of manner.
So this is sort of a naive definition.
Yeah, this is a naive definition. This is kind of the first attempt that we make at trying to define what randomness is in terms of compressibility. And the reason why this happens very informally is because implicitly, when we're introducing a specific sigma inside of the comogative complexity, we're not only putting information about sigma, but also the size of sigma. Imagine in a Turing machine can go back and forth as many times as it wants. So it can go to the end and then go back to the beginning and have information now about the size of the sequence. The relationship about how this actually gives you information about the sequence is very technical, but the whole point is that the amount of information you're giving is more than sigma itself, than the size of sigma itself. So in a way, for any sort of sequence, there is a way in which you can exploit that extra information to describe sigma in less than its length, basically. I'm not going to go into the details because they're extremely, extremely complex. But basically, the reason why I'm telling you is because now we're going to eliminate that possibility, and we're going to give a Turing machine only the information about just the string and not its length. And we're going to see how we're doing this. And to do this, we have to introduce the notion of a prefix-free set. Okay, a prefix-free set is a subset of a set of finite strings.
Sorry for beating a perceived horse here.
It's okay.
Because it's written down. I just want to make sure what exactly is the dependent one and what is the non-dependent.
My bad. I should have written it properly. C. What do you mean C? This C?
Yeah.
Just dependent on the choice of U.
Okay, then M should also.
Okay.
Sorry.
Sometimes people just write C of the number of variables that it depends on.
Oh yeah.
C of M.
Oh no, here, this one depends on M.
Oh, capital.
This is, that's the thing, this comogative complexity is the one that we defined at the beginning. This one is the one that is for a choice of U, but we don't write U because we drop because when we define the thing, we don't care about constant, so we don't care about the encoding, so we just drop the U. Either way, back to prefix-free sets. This set here is prefix-free if the following is satisfied. Sigma being in S implies, sigma being in S and sigma being a prefix of theta, as in, for example, we could take sigma to be 0, 1 and theta to be 0, 1, 1, 0, 1, right? Here, sigma is a prefix of theta. If this is the case, if theta is in S and theta is a prefix of tau, what have I been saying for this? I don't know. For tau, then tau is not in S, right? we basically want to avoid strings that are contained at the beginning of any other string, right? And the reason we do that, or specifically we want this to be true for basically, we say that a Turing machine is prefix free if its domain is prefix free. What does this mean for a Turing machine? Basically, when we say the domain of a Turing machine, we kind of mean the set of thetas that it will allow and that it will actually compute things for. As in, anything else, it would just basically not halt. It doesn't give us any sort of result, or it will reject the string. So what does this exactly do? In an intuitive manner, what it's trying to do basically, it's converting all of the Turing machines into a Turing machine that can only read and move in one direction. If you think about it, a Turing machine that has this sort of string could behave differently depending on whether it sees this or whether it sees this, right? However, a Turing machine that has a prefix-free domain will first see the first one and will have to immediately just, sorry. This is a rather confusing notion.
So it says if sigma is an S,
Mm-hmm.
then what?
If sigma is an S and sigma is the prefix of some other string, then that string is not an S.
Okay.
As in S, there is no two strings, such as one is the prefix of the other.
As in, like, one string is contained
At the beginning of the other one.
Beginning, okay.
Necessarily at the beginning. This doesn't count. As in, like, if sigma was 0, 1, this wouldn't be the case. Sigma would not be a prefix.
Okay, so then S can only consist of strings that start with 1 and start with 0? Is that what you're saying?
No, let's construct let's construct a prefix-free set. Let's consider S to be prefix-free, and we will consider this one, for example. Right, this one is prefix-free, whereas this one is not. Why? Because this one is a prefix of this one. Yes? So just think in terms of a Turing machine. What does this mean? Restricting the domain of a Turing machine to be prefix-free, it is equivalent to restricting the machine to be a type of machine that can only read its tape in one direction. As in, it can only see the input that it's seeing, right? If you input sigma into the machine, imagine sigma is some like 1, 0, 1, 1, 0, 1, right? The Turing machine is only able to see this digit. And once it moves to the second digit, it cannot go back nor see that, or it cannot go back. So it has to just keep moving and see. So in a way, what we're restricting is the fact that the machine will never be able to have any information about the length of sigma. The very problem that was allowing for this to happen was this, that we were giving more information than just sigma itself. We're giving the length of sigma also as the information, right? But now, by restricting the Turing machine to be one that can only move in one direction, if you think about it, you're just taking a machine, giving it a 1, the machine does something. Then giving it a 0, the machine does something. But the machine has no information about what the rest is going to be. This is what we're actually restricting by preventing this. The implication is a bit subtle. It's not immediate. That's why I'm giving the kind of analogy of the machine only going in one direction. But the whole point, this is kind of like a subtlety. Just think that we can fix now our notion of complexity, and we're going to come down with a different notion. It's going to be called the prefix-free. The prefix-free come-over of complexity. This is a different notion of complexity. I'm going to define it here, actually. Is this visible? Yeah? Okay, I'm going to define it here because I want to use this definition later. A prefix-free model of complexity is the exact same notion as before, just except of using Turing machines, we use prefix-free Turing machines. That is a special restricted type of Turing machine that will allow us to actually distinguish the strings from each other. So here, a prefix-free model of complexity for some particular string sigma is going to be defined like this. Again, we could define it in terms of machines, but we're again doing the same exact trick of just using the universal Turing machine. So imagine this is for a fixed universal Turing machine. It's going to be defined in the exact same way. It's going to be the minimum string such that t in the natural numbers, such that t is a finite string. Then this we're going to call v. This is going to be our universal Turing machine of tau is going to be sigma, where specifically this Turing machine v is just going to be prefix-free. This is the only restriction we're putting. And when we define it this way,
So is it necessary that a Turing machine that is free can be a prefix-free machine? We can construct a prefix-free universal Turing machine?
well, yes, but it will only be able to kind of simulate prefix-free Turing machines.
Okay.
But yes, it is. When we say a universal prefix-free Turing machine, we're referring to the universal Turing machine. We're not saying that the Turing machine is prefix-free, which I don't know actually. I don't know if it is prefix-free, but it simulates all prefix-free Turing machines and only prefix-free Turing machines.
Yeah, I don't see why the coding of the other Turing machines has to be in a prefix.
Hmm?
I don't see why the universal Turing machine itself has to be prefix.
Mm-hmm. I think I'm missing a page. But anyway, now that we change it, we literally just change the definition of the prefix-free model of complexity to be like this. We change the notion of how we're measuring now the complexity. And now we say that a sequence omega is random if and only if there exists such the prefix-free model of complexity of that string given the first n digits is going to satisfy that it's going to be bigger than n modulo that specific constant. And it actually just completely circumnavigates all of the issues that we had before. And actually, it was proved, I think, by Chatin and Levin, I think, that the set of strings that satisfy this has actually measure 1. That is, the number of infinite sequences that are random, according to this definition, is unbelievably bigger than any other sort of sequence. And yet that's basically a definition. Any questions?
Sorry, let's plug in the definition.
No worry.
So for the first set, if I add the string 0, 1, 0, would it still be prefix-free?
The first one?
Yeah, that first set. If I add the string 0, 1, 0. You already have 0.
You already have 0. You can't add that.
Okay.
Yeah. So for example, when I add, if my set has the element 0, then it means it will not have any string that begins with a 0.
Yeah, okay. So
right?
once I specify, so I can only have one of.
No, okay, Claudia, can you add another 0 next to the first 0 in the set?
A 0.
Just 0, 0. It says just 0.
Now you can actually have 0, 1, 0.
Oh yeah, you can.
Okay.
Thank you. So yeah, we're kind of out of time. I was going to go into the unpredictability paradigm, but I think I'm going to skip that and just basically talk about very fast that after seeing this, basically, we have two other notions of randomness that are actually equivalent to this. So the actual name that we give to this is the type of randomness that is called Martin-Loaf random. It was actually proved by, Chaitin proved that the measure was 1. Chaitin and Levin proved that this type of randomness is completely equivalent to Martin-Loaf randomness. That is the type of randomness that we will define when we explain the measure theoretic typicality paradigm. Okay? This has also a different name that is also the same notion as 1 randomness. And just know, the fact that there's a 1 here just tells you there's perhaps a 2 randomness and a 3 randomness and a bunch of other randomnesses. But this is kind of the first one that was established. It is the basis for what the rest of notions of randomness is based on. And actually seeing how they differentiate from each other in terms of the paradigms is actually quite interesting. And how completely different areas of math end up coming up with exactly the same definitions. So yeah.
So you said for Martin-Loaf randomness, you can pick a string with probability 1, but with probability 1, every string is
Mm-hmm.
Martin-Loaf. Okay.
Yeah, actually, very like the way we actually construct Martin-Loaf randomness in the measure theoretic typicality is by basically looking at the string and saying, oh well, if that string does not belong to any string that has quote unquote effective measure 0, that is basically that it's very unlikely that it's actually going to happen in a random process. If that string doesn't belong to any of those sets, then it is random. So this fact is actually not that surprising when you study the actual definition of where Martin-Loaf randomness came from.
Which came
from measure theory. It was developed.
He cares about the measure of the set in order to randomness. And here, you start with the definition of randomness, realize the
Yes, exactly. Well, in measure theoretic typicality paradigm, the randomness is dependent on the measure too. Like this is why the notion of randomness is not an absolute notion. It depends on the actual construction that we're making. But in the standard kind of measure, the Lebesgue measure, these completely coincide. Any other questions? Oh, yes. Thank you. Any questions? There were a lot of questions. Oh, okay.
You said you were going to talk about applications.
I have a whole part of applications. It's not really applications, but like the fact that we constructed this notion of complexity, because here it kind of is just out of nowhere, like, oh yeah, this is just defines randomness. But the notion of comodo complexity is extensively used in just computability theory. First of all, this notion of complexity, only in logic, was I think it was Chaitin again proved created a proof of Gödel's first incompleteness theorem just using the notions of complexity, and more recently there was also a proof of the second of Gödel's second incompleteness theory, also just using notions of complexity in this way. Other areas, there has been this thing called the incompressibility method, and it is basically the use of what now we know as random sequences in order to mimic the average behavior or typical behavior of a random event, and thus you are able to get average times for computer programs, right? Basically the notion of the fact that we are able to measure randomness in some way allows us to compute things that are very random and test computers with them. Like what happens when you give something that is actually extremely random to a computer? How's that compressing program behave, right? And apparently it's been used in areas like combinatorics and formal languages, as well as circuit complexity and stuff like that. But it has actually also had, I don't know if it's a bit, well, it has also had not applications, but just this actually has appeared in analysis. And it's basically, if you know the basic result in analysis that says that every non-decreasing function from 0 to 1 interval, thank you, from the unit interval into R is differentiable at almost every point for almost every x. Well, if you consider this very result, it was showed that every non-decreasing function for which it is basically every non-decreasing computable function, the x's for which it is actually differentiable completely coincide with the ones that are computably random. And when you exchange the notion of non-decreasingness to having a bounded variation, then the x's that completely coincide to the ones that are differentiable are exactly the ones that are Martin-Low random, surprisingly. So the concept itself kind of arises in different places, and it also has applications in actual building notions of computability. So yeah.
And computably randomness really just means it just spits it out.
Basically, it's kind of approximating notions of random. I actually don't know what the exact definition is, but yeah, this is a stronger kind of thing. It's more practical. The notion of computably random is more practical.